Trying to comprehend how big the universe is one of those questions that astrophysicists grapple with all the time. Trying to explain it in a way that's easy to understand, well, that's a whole other challenge. In 1977, Charles and Ray Eames, hugely influential American designers, released one of the most elegant and creative pieces of science communication of modern times, Powers of 10. It took the viewers on a journey from a picnic blanket near Lake Michigan to the edge of the known universe, and back again. Over 40 years later, as a humble homage to this groundbreaking film, we're going to take a similar journey through time and space and see how our understanding has changed along the way. As in 1977, we'll start with a picnic, though this time we're on the island of Sicily in Italy, rather than Lake Michigan. We'll start with a scene 1 metre wide, viewed from 1 metre away, and every 10 seconds we're going to move out to 10 times further away, so the scene will be 10 times wider. This square is 10 metres wide, and in 10 seconds the next square will be 10 times that. The movement may seem linear, but we're actually accelerating exponentially into the distance. This square is 100 metres wide, the distance someone can run in 10 seconds. Well, if they're running at 43 kilometres an hour, just under the speed of your cat. 1 kilometre. Though our picnickers are indistinguishable now, we can still clearly see the impact of human activity on the world. 10,000 metres, or 10 to the 4 metres. This is the distance a supersonic plane travels in 10 seconds, and we're now reaching the highest altitude flown by such a plane. 10 to the 5 metres. This is the distance the International Space Station travels in 10 seconds. There it goes. From here on, human activity will be lost to sight. We're at the scale of countries. 1 million metres, or 10 to the 6 metres. We've long left Earth's atmosphere, and soon we'll see the whole planet. What a jewel. 10 million metres. The invisible magnetosphere shields us from the dangerous ionising radiation of space. 10 to the 8 metres. This line extends at the speed of light. This is the time it takes for light to reach us from the moon's orbit, the age of moonlight. The Earth is now just a pale blue dot in a sky full of stars. Even as we accelerate away, the stars appear stationary because they're so much further away. So much empty space. Let's illustrate the orbits of the planets in our solar system, otherwise this could get a bit dull. Here comes the orbit of Venus, then Mars, and now Mercury. Since 2010, the NASA Solar Dynamics Observatory has been using an extreme ultraviolet filter to monitor the activity of our Sun. Finally, we reach the orbit of the outer planets, the gas giants, but just specks at this distance. There's the orbit of Pluto, one of the dwarf planets of the Kuiper Belt, 10 to the 13 metres, and we're moving out of the solar system. In 2012, the Voyager 1 spacecraft became the first human artefact to make this journey, followed in 2018 by its twin, Voyager 2. Both were launched in 1977, the year the Eames were working on Powers of 10. We're heading into interstellar space. Our Sun is just one of billions of stars, and still at this distance, the night sky looks very similar to what we see at home. This square is 10 to the 16 metres, the distance light travels in 1 year, 1 light year. Here's our closest neighbour, Alpha Centauri. 3 stars for the price of 1, with planets orbiting around them. I'd love to know what's going on there. Thanks to data collected by the Gaia spacecraft, we're building a detailed 3D map of the Milky Way. There are between 100 and 400 billion stars in our galaxy alone, and clouds of dust and gas like these nebula where new stars are born. Images sent from the Hubble Space Telescope have been blowing our minds for a generation. As we move away, we begin to see the great flat spiral of our galaxy, a few 100 billion stars rotating around a black hole, Sagittarius A star, 4.2 million times more massive than our Sun. We now think supermassive black holes reside at the centre of nearly all galaxies. These 2 dwarf galaxies are the Magellanic Clouds, which together with at least 80 others make up what's known as the local group of galaxies. 10 to the 22, 1 million light years. Soon we'll pass the supergiant elliptical galaxy M87, and if we switch to radio waves, we can glimpse the supermassive black hole at its centre. Switching back to visible light as we traverse the Virgo supercluster, each tiny dot, not a star, but a galaxy. Billions of stars floating in an ever-growing void. 10 to the 24 metres, the limits of our vision in 1977, but over 40 years later, we can show a bit more. Clusters of galaxies arranged along filaments, like the Pisces Cetus supercluster complex. At 10 to the 26 metres, we switch our view to microwave, and we can now see the current limit of our vision. This light forms a sort of wall all around us. The light and dark patches show differences in temperature by fractions of a degree, revealing where matter was beginning to clump together to form the first galaxies shortly after the Big Bang. This light is known as the cosmic microwave background radiation. 10 to the 27 metres, 1 followed by 27 zeros. Beyond this point, the nature of the universe is truly uncharted and debated. This light was emitted around 380,000 years after the Big Bang. Before this time, the universe was so hot that it was not transparent to light. Is there simply more universe out there yet to be revealed? Or is this region still expanding, generating more universe, or even other universes with different physical properties to our own? How will our understanding of the universe have changed by 2077? How many more powers of 10 are out there? From a picnic blanket on Sicily to the very edge of our understanding, I salute the Eames for the way they told this beautiful story, the story of the universe.